Thanks, Marco, for invitation, and also thanks for people from Griff's coming to the talk. Yeah, I guess it's the first CQT joint seminar, if I'm correct. This is a recent work studying the complexity of non-locality or Bell inequality, and it's a joint work with and Tara Zhang, Thomas Wittig, John Wright, and Henry Yuan. So that's a more succinct title of our paper on MIP star and RE are two complexity classes. And we show that these two classes are equal, so they contain the same set of problems. So that's a complexity theory result and provides some perspective on physics and mathematics that you will see. So I'll give you a very high-level brief history of the problem, and it will consist of three parts. The first part is about computer science. So around early 30s, the question of what is computation has been studied, and there are several different models being proposed, and like Turing machine is just one of them, and these models are shown to be equivalent. And a very simple problem called halting problem. To given you an algorithm, whether the algorithm halts or not, or given a Turing machine, whether the Turing machine halts or not, is called halting problem, and that's going to be undecidable. There's no algorithm that you can solve this simple problem. And in the 70s, because now you have computers and how to efficiently solve problems becomes important, and there's a theory called complexity theory being developed. But most relevant to our research is an area called proof verification. And so this list of capital letter combination is different models of complexity different complexity classes motivated by the concept of proof verification. The most famous one is MP. I guess you must have heard it at some point, and the class that's relevant to our work is MIP. These are multi-interactive proofs, and also technically we rely on a theorem called PCP theorem in complexity theory. It's like motivated by the research on MIP by decreasing the size of the problem, downsizing the size of MIP star characterization to get the PCP theorem. So proof verification is really a key in that line of development and also in our work. So I'll just give you a very brief introduction of what it means. So for MP, you have a prover and a verifier. And the way it works that you have a prover want to convince some statement to the verifier. So some statement is true, some statement is true, and with some proof. And the proof is sent over from the prover to the verifier as a written string. And then verifier checks whether to accept or reject. We need two conditions, completeness and soundness. So for all correct statement, there should be a proof for the prover to convince the verifier. And for false statement, there should be a proof, and that's the soundness property. So that defines, so if verifier is deterministic polynomial time verifier, then it defines the class NP. And it's a big open problem. What is NP? Is it equals to P or it's different from P? A natural generalization of this model is when you consider interaction. So now the prover can communicate with the verifier, and there will be multiple rounds of communication. And in the end, the verifier would determine to accept or not. So that's called interactive proofs. And we do know that the set of languages that have interactive proofs is equal to P-space. And that's a major breakthrough in the 90s in classical complexity theory. And it's surprising because like P-space is a polynomial space. What the set of problems you can solve with polynomial space is a very different motivated model of interactive proof. And the further generalization of this proof verification, you consider two provers. And it's important now that the provers themselves, A and B, Alice and Bob, cannot communicate with each other once the game starts. The verifier would send questions to the provers, and the prover will respond. So that class called MIP will also have a characterization MIP equals to NX, non-deterministic exponential time. So it's like an exponential larger version of MP. And we know that it's different from MP. So it's so adding interaction and adding extra prover, we know that the power of the model is stronger because there's no result. So that's a very brief introduction of the proof verification model. And so I guess the celebrated breakthrough of that line of research is called probabilistically checkable proofs. And in the PCP, you have something like this. So this is like a proof and of like bit strings. And this is the verifier. And it's probabilistic because the verifier would flip some coins and determine where to look at the proofs. And so this R parameter here is the number of randomness the verifier uses, and Q parameter here is the number of bits that the verifier reads from the proof. The PCP theorem then says that for like a statement of size n, there is a format to write down the proof so that the verification can be very efficient in the sense that the verifier only need to flip random bits of the size log of n. And to remember that this is proof of size n, so to index, so to specify which bit you are talking about, need log n bits. And the number of bits you need to look at from this string is order 1, so it's a constant. So that's a very surprising result that for all statement in MP, you can have probabilistic checkable proof of this form. So it's really efficient. You only need to read constant number of bits from this very long proof stream of n bits. And that's a main advantage that we will exploit in our construction. And PCP theorem is, as I said, it's a really a key breakthrough in complexity theory, and it's also has like it's a theoretical result, but also has a lot of implications in other areas in computer science, like hardness of approximation and also delegation of computation. And in quantum computing, though people have been studying quantum analogs of, for example, the class of PCP, and it's still a main open conjecture whether, like, there's like in the Hamiltonian complexity model, whether there's a PCP theorem holds for Hamiltonian systems. And so that's a very brief introduction of connection to computer science. And in physics, I guess people are more familiar with this part. So it's starting from the paper of EPR in 35. And I guess like Einstein called this phenomena spooky action at a distance, and it's later named entanglement, and also like lead to a debate between Einstein and Bohr of the completeness of quantum mechanics. And they have like a paper published in the same year in the Physical Review debating this question. And like it's interesting to see that even scientifically the paper by Bohr is more scientifically correct, but if you look at the citations, the EPR paper is much more influential, and we name this particular state as an EPR state, and we will use this state as a source of randomness generation for our particle. And but the debate has been around for many years until John Bell come up with this genius inequality, later known as Bell inequality. So, and this is very simple inequality, but it's very important because it tells, like gives you a very concrete mechanism to tell, or experiment to tell apart the classical mechanics from quantum mechanics. And later there have been interesting developments, and we will mention one result by, or conjecture by Tsirelson, who proposed the question, which is very fundamental to our problem, whether you can, like, this is like you want to understand the correlation between remote parties. Does it matter to consider finite systems, or you have to consider infinite systems, whether these two setups are the same or different? That's Tsirelson's problem, and we will later come back to this problem again. And that's the connection that we will mention in the physics part. And to mathematics again in the 30s. I guess it's not a coincidence, because von Neumann was trying to lay the foundation for quantum mechanics and quantum field theory. He invented some algebra theory, operator algebra theory, later known as von Neumann algebra. And also, like in mathematics, have been rich development, basically characterizing or classifying what are different kinds of von Neumann algebras are there. And in that process, Alan Kong proposed so-called COM embedding problem. It's in his earlier paper in the 70s. At that time, it's not a big problem. It's just mentioned in that paper as a conjecture. But later on, people found out that this problem is equivalent to many other problems, and now it becomes a central problem in operator algebra. So in recent years, there have been many conferences dedicated to this problem. Like mathematicians are really interested in understanding this problem. And so there are equivalent problems. Some known problems are Kirchberg's QWEP conjecture, and also the Tsirelson's problem that we mentioned earlier. And the equivalents are known in our community, like people in quantum information theory or mathematical physics has been proven that Tsirelson's problem and the quantum embedding problem are equivalent. So they have the same, like, true, if one of them is true, the other, so is the other. So that's what we have been talking about. We have used or listed several techniques from computer science, and we will use them, and also quantum information theory techniques to prove problems in physics and mathematics. So I guess that's a very high-level overview of what we will be talking about in this talk. So now I want to dive in to give you a much closer look of what we are doing here. So the class MIP star is much like the MIP. Remember the model that we talk about, two-prover interactive proof system. You have Alice and Bob, and talking to a verifier. They want to convince the verifier of some statement. But now the difference is that we allow Alice and Bob to share entanglement. So Alice and Bob can share arbitrary entangled states, but they cannot communicate. So in this paper, Cleve, Hoyer, Turner, and Waters in 2004, they systematically studied this complexity class and connects multi-prover interactive proofs in computer science to Bell inequalities.
So can I ask a question at this point? So when we've got two provers, how do I think of this in in a computational sense? Does this mean two computers that are jointly computing the answer to some problem, or what?
Yeah, you can think of like there are two computers in two separate labs. They have input and output channels. So the verifier sends out questions, like in a Bell test setup. You have questions for Alice and questions for Bob. It is important that Bob doesn't know Alice's question, and Alice doesn't know Bob's question. And they have to respond. So this is like input-output procedure. You have to, this is some computation you can carry out. There's no like limitation of what you can do on Alice's side. You see this question and you have to respond with an answer, and then the verifier would accept or reject. So these two provers are two computers. You can think them as two computers that far apart. They cannot communicate with each other. They cannot tell, Alice cannot tell Bob what the message been sent to her previously.
Okay, and
Robert,
so
otherwise they have, sorry.
Oh,
sorry, you go ahead.
So sorry, so the class, so the point is that the class of it, there's no restriction on the computers. This is just the class of problems that can be verified.
Yeah. So the limitation is on the verifier side. Alice and Bob is all powerful. We don't have any computational limitation on them. So but it's not trivial, like, because it's not all problems is in this class, because verifier has to be able to detect errors, right? If you are trying to fool me, then I have to have a strategy to tell that you're making you're doing some tricks. That's the way that it's non-trivial.
Yeah.
Okay. So very good questions. And in that paper, they realized so-called soundness problem, which will come back later. So the soundness will become a problem because of entanglement. And that's a very easy observation. And more importantly, I guess, the connection between MIPs and Bell inequalities open the door to the development of quantum analogs of powerful ideas in interactive proofs. Like in classical computer science, there have been a lot of work or techniques that are very non-trivial, like low-degree tests, parallel partitions of games and PCPs that have been seen before. We can use that in studying Bell inequalities now. And so to be more concrete, we define a concept called non-local games. These are very simple objects. So we have X and Y are finite sets and answer sets A and B. And also you have a distribution over this joint a space X, Y, and then a decider. So given question and answer pair, you need to decide to either to accept output 1 or reject output 0. So that's a very simple, because it's finite set and also everything is finite, and that's a local game. And we will also consider families of games specified by Turing machines. And then verifier is in a pair of Turing machines and a sampler and decider. So the sampler Turing machine is, as the name suggests, is generating the distribution. And you can think of the process as you have some random seed Z and apply some function LA and LB to get the question for Alice and question for Bob. So the Turing machine S is taking care of how to compute LA and LB. And then decider is simply the decider in the non-local game. And there's an N, which is index, so which size or which game in that family you are talking about. So N will be from 1 to infinity. And then the nth game would be the game defined by Sn and Dn, the samplers of this fixed index. So that's some terminology that we'll fix. And so for a game, we can define two values. One is called entangled value. So an entangled strategy is like a tuple of state and measurement. The state is in the tensor space, and Alice and Bob has measurement. So for question X, I do a measurement to get outcome A. That's all this, all Alice and Bob can do. And then the value is in the soup of the maximum of all possible strategies. And that's the expected probability of Alice and Bob's winning probability. The expectation of the winning probability given by the quantum mechanics. So that's the value, entangled value star. And then the class of MP star is roughly speaking, approximation of this value. This is a value between 0 and 1. It's a probability. I want to know, like given the game, I want to know the value. Like in the Bell setting, given the CHSH game, I want to compute this magic number of 85%. Okay, so but we'll be interested in another value. So that's called converting operator value. So you have a single Hilbert space, but now Alice and Bob they use converting operators for all question and answer. And then we define a converting operator value. So very similar formula, but you don't have like tensor structure, so you don't have tensor product between the operators. And still you're maximizing over all the strategies of this probability the players can win. Now the Tsirelson's problem that we referred to earlier is then, is this two definition same, like give you the same game value for all games? It's interesting to mention that if like this Hilbert space is finite dimensional, then they are the same. So commuting operator can be, you can prove that the commuting value, because the structure here can be, you can show that it's a direct sum of tensor structures, so it's the same. So the problem would only be interesting if the Hilbert space H is infinite dimensional, but like fortunately we won't be talking about machineries of how to handle like infinite dimensional operators and Hilbert spaces. We were always working with the entangled value, but the consequence is like we'll see this from these two algorithms. There are two algorithms known for these two values, the entangled value and the commuting operator value. So the first algorithm is very easy. You just do exhaustive search for better tensor product strategies in that, like for that value. You can increase the dimension of the space or and use higher precision. You like do an epsilon net of this strategy space, and you can approximate this value from below, right? Interestingly, there's another algorithm which is much more non-trivial. This is also known in the literature as NPA hierarchy. It's a hierarchy of SDPs, which gives us values that approximates the commuting operator value from above. So algorithm 2 would give you a sequence of values that are decreasing and converge to this commuting operator value. So now if like Tsirelson's problem has a positive answer, meaning that these two values are always the same, then we do have an algorithm for approximating this entangled value, because what you can do is you would be able to alternate in between algorithm 1 and algorithm 2, and they will converge to the same number from below and from above, and that is sufficient to have an algorithm, even though we don't have any bound on the complexity of this algorithm. But at least there will be an algorithm for approximating this value. So given any epsilon, I would be able to tell you that whether the value, what the value is with an error of epsilon. So that's a complexity theory consequence of Tsirelson's problem having a positive answer, meaning that MIP star is then in R, which is a subset of RE. And so that's the setup that we have been talking about, and I would, if there are questions, it's a good time to ask, because in the following slides I will tell you bit like what's the most recent outcomes or research happening understanding the power of MIP star.
So
yeah.
okay.
I'm sorry. Yeah. Can you just explain a bit more the relationship between MIP sharp and the entangled value?
So you mean the relationship between MIP star and the entangled value?
MIP star. Sorry. Yes.
Yeah. So in the previous slide I mentioned that the MIP star is roughly the complexity class of approximating this value, but like we have to make something explicit, because like there is a size that we need to talk about. Like we need to specify like what is the question size. So basically the X, Y, and AB, the size of these sets, we want to make sure they can be encoded in like length and bits. So that's one technical detail that I'm hiding here. So basically, if you have a game and you want to compute this value, and that will be MIP star, but it's of some different size maybe. You have to, you have to think about the size. Yeah.
No, I think my question was a little bit more basic than that. It was that you define MIP star as the class of languages that can be verified by
so MIP
by
star
verifier that with provers we having some constraints. Why is it that it's equivalent? Yeah, why is that equivalent to calculating?
I think I'll get your question. So MIP star is injectable verification protocol, and we need completeness and soundness. So for yes instance, we need the value to be high, right? So the language, starting from a problem, we have a game, the injectable protocol, and the game is yes instance, and the value will be high. And if the problem is a no instance, we want the game to have a low value. That's the correspondence of MIP star is a set of languages, and the languages, each language would define a game, like instance of a language, like given me a problem and of the language, I would convert it to a game. There will be a protocol for this particular problem, such that if the problem is a yes instance, the value of the protocol is high. If it's a no instance, the value of the protocol is low. So therefore, if you are able to approximate the value for any protocols, then you would be able to solve the problem that you start with, whether to decide whether it's in MIP star or not. Is that clear?
No, it's not entirely clear, but that's okay. I guess I'll just have to
can I ask a question? I mean, is the star in MIP star just means there's entanglement present?
Yeah, star means entanglement, because like classically there's MIP and just to emphasize that now the provers can share entanglement, but nevertheless the messages they exchange is still classical. So from the verifier side, it's the same. It's the same. You just send out classical bit strings and receive classical bit strings. But how do you define what the provers can do is now different. The provers can share entanglement state, like entangled state, and do measurement, and they can end up with stronger correlations than classical setting, right?
Can I ask? Sorry. Can I ask another question on these slides? These claims about convergence.
Yeah.
I mean, I know where you're going is towards these uncountably infinitely large Hilbert spaces, etc. I mean, how presumably, I'm just surprised that you can make the presumably with confidence claims about convergence in such extreme Hilbert spaces.
Yeah.
I don't know. Can you comment on that?
Yeah. So we only work with finite dimensional stuff. But the consequence, but the consequence here, like, is actually from this line. There's two algorithms that we know. One of them is interesting. One of them is trivial. But nevertheless, these algorithms give you converges to these two values. So if Tsirelson's problem has a positive answer, but we don't directly attack this value other than this known algorithm. If this problem has a positive answer, then we have an algorithm for this entangled value that's defined as a limit of finite dimensional strategies. There's no like. In the maximization, we can consider there's no upper bound on the dimension that the provers can use, but each time it's a finite dimension Hilbert space, and then you can take the limit. It's not like you don't start with from infinite dimensional Hilbert space from the beginning, but so yeah, because the definition of the value star is the supremum of all finite dimensional strategies. That's how it's defined. But nevertheless, we can see consequences because of this known connections that we previously known in the literature. Like if Tsirelson's problem has a positive answer, then we know that this value is decidable. There is an algorithm, but what later we'll show that there's no algorithm for this value. Therefore, you cannot have this situation where these two algorithms converge to the same value all the time, and therefore Tsirelson's problem is false. It's an indirect argument, but later on we will show that it's possible to explicitly construct a game to separate these two. You can think of this as convex sets and enclosed convex sets, and it's possible to separate these two sets. Yeah, there's some other question.
Yeah, so just to clarify, is it that so the verifier is encoding the question if it wants to decide whether a certain string is in a language, then it's encoding the XY the same into
no. The language is known to both the prover and the verifier. So suppose that they always want to solve for example, maybe I don't know what's your favorite problem. Let's say it's graph coloring problem. Like we have a very big graph, and the prover wants to convince the verifier that graph is recolorable. That's kind of a problem. And for that problem, we have a game. For example, the verifier can randomly sample an edge and ask what are the colors of these two vertices and show me the colors. Of course, that's not a good approach because the prover can always cheat. Like give you a different pair of colors, and then the prover always wins. So that's not a good game for the coloring problem. But you can think of the correspondence like from a problem, I can define a game. So that if the problem is a yes instant, the game has a very high value. You can also assume that it's perfect value.
Right. Okay. Yeah. So then in a given round, the verifier doesn't get the answer. The verifier has to collect statistics and check whether the probability is higher than such a number. So the verifier will have some probability of verifying.
Yeah, we just study the probability, so we don't need to run it many times. We just study the probability. Yeah. In reality, you need to repeat the game to increase your confidence. Yes. Okay, so I've spent a lot of time. Maybe I should speed up. So I'll give you a very quick overview of 3 stages of MIP star research. So in the beginning, like in the first 5 years, there's not much known other than that there will be a soundness problem. The soundness problem is because like once you have entanglement, the players can play more tricks. The strategy space is much bigger, so they can achieve higher value. And the soundness of a classically sound proof, meaning that you have like an interactive proof without the entanglement, which is sound. In the no case, the value is very low, but in that case, with entanglement, the value could become bigger. And that's a soundness problem. So there could be classically sound interactive proofs that are not sound quantumly. And there's this game called Magic Square game is exactly giving an example like this. So this is like very simple game. You have like 3 by 3 table with 9 variables, and each row has odd parity and column has even parity. And classically, there's no solution, and you can define a game out of it. And this game is classically sound, but it's not quantum sound, as you can have a perfect strategy using 2 EPRs to win the game. And that's an example where the soundness can be broken with entanglement. So that's a big problem for interactive proofs, because now we don't know whether classically sound particles are quantum sound. And indeed, there are certain models where this problem is unfixable. Like if you consider XOR games, where the decision is depending only on the parity of the player's answers, then this power of this entangled interactive proof with 2 prover XOR games is much smaller than the classical one. So there are some other examples, and that's an interesting perspective that sometimes entangled causes a problem, and it's like an unfixable bug. And later on, people have developed techniques to fight against this kind of problem, soundness problem, and there are several different techniques that you can use. And important to us is linearity test, multilinearity test, and low degree test. And that's led to a breakthrough of Ito Vidic in 2012, proving that at least with a star, the class is not smaller. So in some sense, the bug is fixed. Later, there have been ideas that you can actually use entanglement. If you consider entanglement powered particles. And the first thing that we can do is to design games for QMA, because like classically it's MP harness, and we know that there's quantum analog of MP and conjecture they are different. So the first step is we were able to prove that non-local games are QMA hard. And that's a technique using quantum error detecting codes plus rigidity. I don't have time to go through rigidity. It's based on the statistics of a non-local game. You can infer the structure of the measurement structure of the prover. And later on, try to improving this QMA lower bound. We developed a technique called compression of quantum interactive proofs. So starting with a large particle, you can end up with a smaller particle, but simulates the larger one. But there is a problem of this procedure is the gap or the precision that you can see or become smaller, and that's something. But nevertheless, it's already like you have you can see a difference between classical and quantum multi-proof and check-proof systems. So that's more recently, there's like QMA harness constant gap results by Natarajan Vidic, and basically what they developed is quantum nano degree test. So it's Pauli basis uses Pauli basis game. Basically, you can command the provers to measure X and Z basis NEPRs. It's a very powerful primitive that you can it's a type of rigidity results as you can see. And more recently, Natarajan Wright proved that this Meeks lower bound, so it's bigger than NX as classical characterization in MIP star. So it separates MIP star from MIP, and you can show that entangled prover can actually prove more. And our work is built upon this work to prove that MIP star is RE. So this Pauli basis game is a powerful primitive that we will use. Basically, it's like remember low degree tests are quantum sound is the techniques that we developed in the quantum resistant set of techniques, and also it combines the rigidity. So now you have efficient self-test of Pauli X and Z measurement of EPRs. And basically, you can have the verifier can send questions like Pauli W, where W is X and Y, so it's constant size. And then the prover would have to respond by measuring NEPRs. So the measurement operator of the provers, LSS operator, when receiving the Pauli measurement, is equivalent to measuring a Pauli Z measurement. So that's tau is the honest Pauli Z measurement, or Pauli W basis measurement. So in some sense, this you can think of this as approximate representation of the Pauli group, and that's the connection that we have to this operator algebra. So even though it looks like we have a lot of techniques from complexity theory, but there's something that we rely on is representation of the Pauli group in that approximate sense. So then the main result is MIP star equals RE, where RE is as hard as the halting problem. So basically, whether you can have an algorithm, if the answer is yes, then the output yes, but otherwise there's no guarantee. A consequence of that is that there's no algorithm that we can approximate this value because it's as hard as the halting problem. The technique that we use to prove this statement is recursive gap preserving compression. So gap preserving compression is already achieved, like in this work. What we need to do is to make the argument recursive, and So that's the consequence of the result is first complexity theory result. We give a complete characterization of a MIP star, and also a negative answer to Tsirelson's problem, because the connection that I explained earlier, that Tsirelson problem would having positive answer would imply that MIP star is decidable. So what do we prove that MIP star is not decidable, and hence Tsirelson problem had negative answer, and build on known connections. Also, Com's embedding conjecture is false. Okay, so maybe I have 15 minutes left. I'll give you a very quick overview of how we give this proof. So the most technical part of this proof is a compression theorem. It's a compression from this very big particle to a small particle, because this one is big because the messages are big. You can think of this as exponential size messages, this as polynomial size messages. It's small because from the verifier perspective, the verifier running time and the messages are much smaller, but nevertheless, the smaller particle will be able to simulate the bigger particle in the following sense. So there is an algorithm called compress. And the compress will take an input verifier V and outputs a V sharp, the compressed verifier. Remember that verifier defined by pair of Turing machines. So V is a pair of Turing machine S and D. V sharp is S sharp, D sharp as compressed verifiers, sampler and decider. We satisfy these conditions. If the big game has value 1, then the compressed game has value 1. If the big game has value less than a half, then the compressed game has value less than a half. So it's kind of a magical compression that you start with a big game, you end up with a smaller game, but nevertheless, the value you can tell the value of the larger game from the value of the smaller game. And also there's entanglement bound. Basically, the smaller game would use at least the amount of entanglement that the bigger game uses, and even there's absolute constant some extra entanglement you need to use. Because in this smaller particle, it's simulating a bigger game. So it uses this entanglement and a lot of extra EPR pairs. That's how we establish this, bound down entanglement. So once you have this magical compression theorem, you can prove the result. So basically what we want to prove is, given a Turing machine M, I want to know whether the Turing machine M halts, terminates or not. So this is how we define the corresponding game for this Turing machine M. So we define Turing machine called D halt. D halt will simulate this Turing machine for n steps. And if n already halts, then the Turing machine D halt would accept. Otherwise, you don't know whether M halts or not. What you can do is you can compute a compressed version of itself. And then you would accept using the compressed decider. So, and here we need to use Kleen's recursion theorem. It's a theorem in computability theory. And basically, I guess like people have seen a lot of uses in high-level programming languages. You write a program and you call itself in the body of the definition of the program. But like for Turing machine, you can do something similar. So even though the Turing machine can be encoded as bit streams, when defining this Turing machine D halt, we haven't even completed defining it, but nevertheless, we want an encoding of this or description of this Turing machine D halt, and that's something that you can do. Meaning that this definition is well defined, and then you can show that there will be an integer n naught, such that for all Turing machine M, if M halts, then this game defined V halt on this index n naught is value 1 if M halts. Otherwise, if M doesn't halt, the value will be small. I guess it's intuitively easy because if M halts in steps, then D halts on index n would know this. But if n, for example, n halts only in 2 to the n steps, then we know that the compressed version of the Turing machine would know this, and therefore, by the definition, the Turing machine default will also detect that M halts in 2 to the n steps. So that's basically the idea to complete the proof. Of course, the interesting part is how do you prove such a powerful compression theorem? So there's 4 steps of construction, transforming the particles or games. We're starting with this MIP star particle with a big question and answer size. And then you do the first step called introspection. Then the purpose of this is question reduction. The question becomes much smaller. Okay. In the second step, you would do oracalization, and that's a pre-processing for the third step, PCP. So basically, sometimes this player would be asked both Alice and Bob's question. So it's an oracle player, knows everything. Both Alice and Bob's question are sent to oracle player, and oracle player has to respond the answers that Alice and Bob could have replied. And then you can apply this idea of PCP, like we have been talking about PCPs. The power of PCP is very efficiently checking proofs. And now what we are doing is we check that the verification here. The verification is still getting very long answers. And then the idea is that the verifier says, well, we'll do a PCP proof for this verification. So don't send this big messages. I will randomly choose locations and check whether to accept or not. So then we would end up with a much smaller answer size. So we achieved both the question and answer reduction. But over the procedures, like we have lose some quality of the gap. So meaning that starting from the gain of gap 1 versus a half, now it's much worse. We want to repeat this game many times. So that's the parallel repetition step to recover the gap. But the idea is that like after repetition, again, this messages will be much smaller than the one that we start with. So we would be able to achieve the compression theorem. The non-trivial part of this construction is an introspection plus PCP. And so basically what this is doing is, like the verifier is saying, oh, I'm lazy. How about the 2 provers come up with the questions yourself, answer the questions, and prove to me that I would have accepted the questions and answers if I was generating the questions. And well, that's a very bizarre situation, but let's see how you can do this. So let's first talk about introspection. Introspection is a technique that first used by Natarajan Wright in the paper to prove stronger lower bound for MIP star. And the idea is the following. So suppose we have a game, and the game is a very big game where we need to sample some distributions in this sampling. Like the first part is a pair of questions, and assume that this Z is a random seed that you can measure using Z measurement on EPRs. So we assume that the player says EPR, so that's something that the players can do. They can sample some random seed, and then the question distribution will be defined by a pair of function LA and LB, right? So in the desirable situation that we want a scenario like this, the verifier only samples intro A to A and intro B to B. So these are like finite size questions. And upon receiving these questions, the player will have to reply a pair Y and A, where this Y is then this introspectively sampled question. So it's LV applied to Z. And this A is what Alice would respond if the Y is the question she received from the verifier. Okay, so both the question and answer is now sampled and measured by the verifier. But now, of course, the question is how would the provers follow this command, follow this kind of prescription? And let's see how we can do this for a very simple class of functions, linear functions. So LA and LB are now linear functions. And to ensure that Alice honestly applies LA, the verifier can perform the following two tests. In the first test, it do some cross-check between intro and sample. So, and in the second check, we will cross-check sample and poly measurement. So because we do this cross-check between sample and poly measurement, and we use this poly basis measurement to enforce that the players had to measure honest Z measurement, and we can make sure that when player receives sample, they have to measure this random seed Z in this EPRs in Z basis, and then compute the question themselves, because Y is computable from Z. So apply some function LA to compute the question Y, and then once you have the question Y, the sample question would also be able to get an answer, because you have the question, you are able to make the measurement for this question and get the answer. So we do cross-check between poly and sample to make sure that Z measurement, this Z is honest Z measurement. And then we do a cross-check between intro and sample to make sure that Y is a correct function of Z, and also that answer A and B are the same. So that's a very easy thing that you can do, but of course that's not all the story. And a very tricky thing is that you want to make sure that in games like two-player multi-prover games, you want to make sure that Alice and Bob, they don't know each other's question. Now this information is computed from this Z measurement on EPRs. So both Alice and Bob can measure on EPRs to get this information Z, and then it will violate this requirement that Alice won't be able to infer Bob's question. So we need another technique, and that's the interesting part. So basically, it's a use of Hessenberg uncertainty principle, and the way we prevent that Alice learning extra information is we sometimes we enforce Alice to measure X on this information to try to erase the information in the Z basis. And if you do some algebra, you would be able to tell that in order to hide this information beyond LA of Z, what you need to measure is this sigma Z measurements for this U in the kernel of the linear function. And with some extra work, you will be able to show that this actually works, so that Alice and Bob has to measure these questions and only see this information Y, but not extra information in Z beyond Y in sampling this question pairs. Okay, so that's how we do it. I will skip the protocol, but it's not too hard to imagine that you would need some cross-check to make sure that the X measurement are correct, and also that make sure that intro doesn't really depend on. So there will be an extra measurement, extra type of measurement called read, where you would measure both this Y and also the X measurement and check that this X measurement information is correct. Okay, so but the question is, linear functions are not enough because they are very special, and you cannot model all the distribution that we want to study to model in MIP star particles. But there's a very simple extension of this called conditional linear functions. So a conditional linear function is a generalization of a linear function where you can do this sequential procedure. You measure, excuse me, you measure a linear function of some subset of the bits in Z, and then you get apply linear function L1 and to get Y1. And then the condition on Y1, you apply some other linear function in some other space. So both the space or the bits in Z, where the bits locates, where the bits locate in Z, and which function you apply, which linear function you apply, can depend on the information that you computed in the first round. And you do this L round, and we call this L number of levels. So in the end, you would output all this Y1 to YK together. So that's how we define the function called conditional linear functions. And you can verify certain things. Of course, we don't have time to do it in detail, but you can check that CL functions can model all the question distributions that we want to use in our situation. And most importantly, the question distribution of the poly basis measurement, the core of the like the efficiency that we get from this poly measurement is CL, and and in the end we only use 8 levels, so number of levels with some constant, and that's simplifies our argument a lot. And so in the end, you can see that constant CL distributions can be introspectively sampled. And that's important because now you can model the distribution recursively. You start with some CL, big CL distribution, you end up with some new game which is still using CL distributions, and that's how we make the compression procedure recursive. And also, if you remember that in the previous construction, we used the same like to input into the compressed Turing machine, we use some Turing machine as sharp, and output is also as sharp. So that's some fixed point that we already be able to figure out because of the properties of CL distributions that we proved. So there are several extra points that one have to take care of. One is that for the PCP technique to work, we need to do this oracleization. And what this oracleization is doing is Alice is doing both Alice and Bob's measurement on Alice's side. And that requires that Alice and Bob's strategy in the beginning uses commuting observables. Like, we are not talking about the Alice and Bob measuring, because in this tensor model, Alice and Bob's operator are always commuting. What we're talking about is if you move Bob's operator to Alice's side, then these operators are commuting. And that's a special technical thing that we need to take care of. Otherwise, we won't be able to do this oracleization step. And then the answer reduction step is easy. We have been discussed. Like the verifier says, you don't send me the long answers. I will do a PCP proof to check that the decider would accept. But of course, we need to do some minor changes so that the question distribution is CL, because we have used this framework of CL distributions. We want to make sure that this transformation won't break the framework. But fortunately, that's also easy to do. So to conclude, what we did is a recursive gap-preserving compression of some normal form two-prover one-run particles. And once you have the compression, you are able to show that RE is inside MIP star. So you can reduce the halting problem of any Turing machine to a particle of whether the value is high or low. And then this equality follows from this containment of MIP star in RE, which is trivially known. And so this gives an active answer to both Tsirelson's problem and Kahn's embedding conjecture. And there are some open problems. So one is, like, can you have a simpler proof? Proof is very long, even though it's modularized, but I guess it will be beneficial to have a much simpler checkable proof. And also there's a complexity class called MIP Co, where your main interest is in the commuting operator strategies. And we believe that this class should be equal to Co-RE, but that's something we are currently doing. Also, there's so our consequence that Kahn's embedding conjecture is false is indirect through known connections. It will be interesting to see whether there's explicit constructions of counterexamples maybe motivated by our construction to this conjecture. So that's some open problems. And I guess it's interesting to mention that after the result is public on the arXiv, we do have some feedback from the proposers of the questions, like Alan Kahn and also Tsirelson. in different ways that you notice that they already realize our solution. And Tsirelson has very nice words about our work. It's like basically we are like it's what we are doing, applying computer science and physics ideas to solve pure mathematical question. So that's it. I guess a bit over time already. So if you have more questions, I'm happy to take that.
Yes, are there any questions, or have all questions already been asked?
Okay, can I ask a question?
Hi, Rahul.
Hi, Zhengfeng. Thanks. Very nice talk. Okay, so I mean, okay, so again, so the places at which this proof, I mean, the classical analog of this proof won't go through. I think one place you said is that the provers won't be able to generate the questions themselves.
Yeah, that's the main reason, I guess. Yes. Yeah. So basically, using EPRs, you can generate like complicated distributions. Even though, like in the classical model, Alice and Bob can share large. We don't bound any shared randomness, but like it's not possible to build interesting distribution upon that. So Alice and Bob would always know Z, and it's not possible to hide information so that Alice knows something and Bob knows something different. And I guess that's where EPR is really helpful, because you can do X and Z measurement to hide information that you don't want the players to measure.
I see. So suppose you want Alice and Bob to jointly sample from some distribution, then I mean, of course, using shared randomness you could do that, but the soundness is the issue, right? And you're saying that you're essentially able to force Alice and Bob to jointly sample from a distribution if they have entanglement.
Yes. If they have the entanglement, basically the introspection is doing that. You have to sample according to the specification of the CL functions that you hide. You only like, because like the answer A that Alice in introspection like in introspection, the Alice or Bob need to reply on both the question Y and A, right? And this Y has to be honest in the sense that it's some function of Z. But more importantly, this answer A only depends on Y. It doesn't depend on other parts of Z. So that's a very crucial requirement that we need to preserve. And that's possible in the quantum setting using EPRs and XZ measurement, but it's not possible using shared randomness. Yes.
So can I ask a question about implications for physics? So I mean, is it still an open question as to whether there's a finitely constructible inequality for which do you get a bound, like where we can say what the bound is differently? What is the difference in the Tsirelson bound between the commuting case and the tensor product case?
Yeah, this is a very good question. So I didn't mention this, but in our paper, we do have like concrete separation between these two values. So there's like something like Bayes inequality that you can tell the difference between whether the system is finite dimensional or it's commuting operator model. there's a separation between these two models. But the question is whether you can realize this commuting operator model in some physical systems that we don't know. So even though like I guess in quantum field theory, people are used to talk about operators that are commuting in a single Hilbert space, but usually there are some extra properties of that theory, like enforces, like give you the tensor structure of the Hilbert space. So that's, we don't know like any reasonable proposal that you can build something in lab and realize this commuting operator strategy to tell that quantum mechanics really should be the commuting operator model. That we don't know, like whether it's purely a mathematical result or it's something physical that we don't know.
But in terms of just a purely mathematical result, I mean, how finite is the Bell scenario, if you like, that you have?
You mean the size of it's huge. It's huge. But I believe that like maybe.
So
even though our result would imply very large size on the size, like the question and answer sets, but I guess it's possible that much smaller sets would suffice.
Okay. So is it so huge that it would not even be easy to actually give an answer to how big it is? Is that the sort of thing we're talking about?
I don't know. It's like 10 to the 100. I don't know.
Okay. That's an answer. Yeah. Okay. Yeah. All right. Okay. Yeah. Okay.
But I mean that's not. I don't believe that that's a problem. The problem is even though that number is lowered down using other techniques, or like if you know that comp is false, then maybe there are different approaches to construct such separations. I guess like operator algebra theorists would know better than me. But whether these operators can be realized in physical systems, then that would be a big problem. Yes.
Yeah. Thank you.
Thank you for the question.
Hi, Zhengfeng. I'm really sorry. You know, something happened to my internet, and then I sort of went away for a while. I'm sorry about that. But anyway, I will. We'll talk offline on that later.
Okay. Yeah. Okay. No problem.
Maybe I would like to ask a quick question about the lower bound on the entanglement in the compression theorem. Is there a simple argument for that?
Oh yeah, it's because
that you really need that much entanglement.
We don't need that much entanglement. We only need some number depending on n. Like if it's n, it still works. Because like in the end, this n will be replaced by 2 to the 2 to the 2 to the n. Like in the proof, it will blow up very quickly. But we need some bounds, like for each n, some.
No, but for the very game you're using, kind of, is there a simple argument that you really need that much, or you could do it by less?
That's in the introspection step. In introspection, you expect the provers to share NEPRs, do measurement to sample the questions. And in that like honest strategy, you have to have this extra EPRs to sample that question. And then you would also need to do this old game. So this old shared entangled state has to be there. And also, in addition to that, you need extra EPRs to sample the big question. So that's the reason that you can establish such a lower bound that you need extra entanglements. Like in the pictures I've used thicker entanglement lines to indicate that even though we are compressing the verifier side perspective, the prover side is even bigger. You need to simulate all this big particle and use actual entanglement. And that's the reason that we can prove some entanglement lower bound in that, like when you do the compression, you expect the provers to share more EPRs, and because it's recursive, so you see that there's no bound of entanglement that would do the job, because you would need more and more entanglement for like when the compression is going forward.
Yeah, it was just a point I didn't get from your presentation today, so I wanted to kind of, I'm pretty sure that you have thought about it, but I was just curious whether there's a simple argument for that. Thanks.
Yeah, it could happen that there's a simple argument, but yeah, we try to simplify the proof, but still we don't have like a major success in doing so.
Thanks.
Thank you.
What can you say about the classes where the verifier has quantum channels where you can use quantum questions through both else and both?
Oh, that's something already known. Like so, most general model called QMIP or QMIP star is where you allow quantum messages to be exchanged and you allow entanglement between the provers, right? And that's known to be the same as MIP star. So quantum messages don't really help you to increase class.
No, I don't mean. I was talking about quantum messages between the provers, or or the verifier encoding the questions in quantum states, which can be done in non-orthogonal quantum states in general.
I don't know, like, because in our model, it's essential that Alice and Bob do not commute. So we don't even allow classical communication. They allow.
Yes, you mean without communication between Alice and Bob, but where the verifier, instead of sending classical questions to Alice and Bob, they can send quantum states encoding the questions. So there's this. That's the
first part. Even though this questions are quantum, doesn't really help. Yeah, it's the same set of languages they can prove.
Right.
And also, like, as a byproduct of the result is having more than 2 players doesn't really help, because it's still RE. But interestingly, we don't know direct proof that how you can reduce, like, for example, a 3-player particle ABC to AB to 2-player particle directly. We only see this because all these different number of players give you the same RE power. So from that, you can argue that the number of players doesn't really matter, and that's the first time that it's been known that have different number of in a classical case, like in the early days, it's one of the first things that it's proven that having polynomial number of players is equivalent to having 2 players. But quantumly, you don't have like very clean arguments. But like, it's related to the question, how if you extend the model, what happens?
Okay, are there any more questions?
Can I just make a comment that it's very nice that you got a reaction from Tsirelson before he died?
Yeah. We realized that like 1 week after he passed away because of cancer. Yes. It's really unfortunate.
Yes. So on this sad note, then let us still thank Zhengfeng again and for this wonderful presentation. And yeah.
Thank you.
Thank you.
Thank you.
Thank you.